Okay, so just coming back to what we did earlier, I did do a typo here. This is supposed to be a k, so this is supposed to be a k here. So this summation that I wrote earlier was much easier to deal with than I first thought. And it will still give us something quite annoying to think about, but it's not as bad as I thought it was. So here, what is the summation coming down to? Well, there's no j in here. So this is equal to k minus 1 times 1 over 2 to the k. Okay, and now we can use this in the definition of expected value. So expected value of this thing is equal to the sum. So from 2 to, so I should say k is equal to 2 to infinity of what? So now remember there is a k here. So it's k times this thing here. Now when you look at that, you start crying because it's not very nice to deal with. So you could use Wolfram Alpha to simplify this thing, and we would be done. So this question is a bit more tricky than I thought, but there is a shortcut around this. The problem here is this k times k. If you don't have this k times k, then this summation you know how to simplify, or I think you should know. So the problem here, we have a k times k, which is not very nice. So again, why not 2 to the j? Because the length here is k still. J does not tell us the length. Right? It's one sequence over all sequences of length 2 to the of length k. So it was my bad. And it's nice that it doesn't explain, it doesn't contain a j. It makes it nicer. So here, if we go back, this probability that x is equal to k is the probability that we stop on the kf toss, which means that this h is the flip k. If we stop on the kf toss, means that we have to have had a tails at some point before here. So to compute this probability, we're partitioning this probability into several subcases. So I'm looking at the position of my first tail. And now I'm thinking, okay, so xj means that my x is equal to k is true, and the position of my first tail, is at position j. So for example, it means that I have something like this. So here, I have tail's head, something like that. And then here, I have my first tail. So here, what I did is I included this last position, the tail before the head, as the position of the first tail, which is fine. It just switches the indices around. So we're looking at a sequence like this, where this is my first tail, and this is the first time I got tail's head. So the whole length is k, and I have a tails at position j, and this is my first one. So now I'm counting how many sequences do I have like this. Well, I only have one of them. Why? Because if this is my first tail, it means that this part was all heads, and if this was my first tails, then I have a head after it, and this would not be my first head. So I have one sequence out of the 2 to the k ones that give me what I want, right? This is fixed, this is fixed, this part is fixed, this part is fixed. So everything is fixed in that sequence. So it's one sequence out of all the sequences of length k. So again, it's one sequence out of 2 to the k ones. So we just rewrite it like this. So the point is that this does not depend on the position of t. That's good, which means that this summation that we're looking at, this partition, just becomes this thing. And now, which means that our expected value becomes k times this probability. Now, the annoying part is that, do we know how to easily deal with that? Well, not really, right? So this is a fine answer. It's just the expected value that we get is a bit ugly to simplify. So if you plug this in Wolfram alpha, what do you get? So the range in this summation is the range over all position for the first t. Yeah, that is exactly correct. In the summation here, this ranges over every possible first position for my t, for my first steps. So can someone write this in Wolfram alpha and see what it gives? If I do it myself, I guess I might as well do it myself. Wolfram alpha. So sum from equal to 2 to infinity of k times k minus 1 over 2 to the k. Hopefully, I did not do a typo. It's equal to 4. With this summation, with Wolfram alpha, you can see it's equal to 4. So my 3 was off. And I think the reason it was off, so here in some other office hours, I did this question. And we proved that this expected value was 3. The reason being, we have, instead of having one outcome, we have 2 outcomes. So it might take a few less fools. So anyway, so what I want to mention is that this simplifies nicely, and you might just not be familiar how to simplify this thing, which is fine. However, I just want to mention, but I'm afraid that mentioning it will confuse you. It's an important theorem. So if we go here, can you guys see my screen in the book? Also, let me share again. So, okay, so if you're interested by another way, so these questions here, this question, and this question. So it's essentially question 6.31 is a very nice question, and it gives you a very nice property. So look at this question. So when you have a random variable that takes integer values to infinity, Well, the definition of expected value is this. You can show that you can get rid of this k if instead of writing an equal sign here, you get a greater or equal sign here. And the reasoning is quite simple, to be honest. Like if you expand these guys, it really makes sense. The number of times you write k times the probability is x is equal to k. When you break these guys down, this will happen a certain number of times. How many times will you get something greater or equal to k? A certain amount of time. So this proof here is not very hard to do, but the principle is very nice. Why? Because it gets rid of one of this factor. So sometimes it's a good trick to keep in mind. When you have a random variable that takes integers value from 1 to infinity, so this trick is very useful for geometric distribution. Here, the point that I'm trying to make is that when we go back to this question, when I go back to this question, I could have used this trick. So instead of writing my definition of expected value, so instead of looking at x is equal to k, I could have looked at x is greater or equal to k. And that can make it a lot simpler. So again, if you're not sure how to deal with k squared in this summation, you can think of this trick. This trick essentially brings down this to only having one factor of k. So anyway, so the whole point of this is that this simplifies nicely. You might think, well, this is ugly, but actually it's not that ugly. It simplifies to 4. So if you want to look, try to do this question with the theorem exercise 6.31. Exercise. That's another way, and sometimes it's a very useful theorem to have. So I'm not sure if you've seen this one in class. I know with Pat, he shows it. I'm not sure with sorry. So again, there was a typo here. This is not a J. This was a J in what I wrote earlier. This is a K, right? This probability does not depend on J. And that's the whole point. There's no J in here. So I'm not supposed to have a J here. So it was a typo earlier that I did. So I'll stick to the problems that I have so far. If you want me to do a problem that I've just shown, I can do it after. But so far, I'll just carry on with the questions, and I can add some other questions after. So because if I start doing proofs, I think there's more important stuff to cover before we do like proofs. Okay, so for the sake of progressing a bit, so we've spent a lot of time on this one. Again, I think the main point is that you should be able to get to this summation. Simplifying it, maybe not, but getting to that point, I think so. I think the main point is to think about this partition idea. It's a hard question. It would be definitely on the harder spectrum of these questions to do on your own like this. Harder part, I think. Maybe even too hard for a written exam. So anyways, let's bring it down a notch. So Lindsay and Simon, so we are back to Lindsay and Simon have a child. This child is a boy with probability a half and a girl with probability a half, independently of the gender of the children. They stop having children as soon as they have a girl. consider the random variables. P is the number of boys that Lindsay and Simon have, and G is the number of girls that Lindsay and Simon have. So we want to find two expected values. Okay, so again, if you think about it, they keep, what is this experiment doing? They keep having children until they have a girl. So it still looks a lot like a geometric distribution. So we will still have to, not quite a binomial distribution. Right, so the point, yeah, so the next break will be around 5:30, yeah. So you might think, okay, I'm counting the number of successes in some experiment. But here you don't know the length of your experiment, right? So here, if you think about it, what is the expected we'll see, but no. So the answer is, like, to be honest, like, I'm not even sure what I'm going to say is right, but let's think about it, right? In a geometric distribution, you know the number of trials that you're making, right? That is a geometric, sorry, a binomial distribution. You know the number of trials that you're making, right? You're looking at n trials, and you count the number of successes. So, yeah, sorry, I misspoke. So in a binomial distribution, you count the numbers of successes in a fixed amount of trials. So it would be an interesting question to ask. So I'm leaving that in the air, okay? Here, if I find the expected number of children that I could have, can I then multiply this expected number of children times the probability of having a boy? Could I do that? So I leave it in the air. Maybe it's yes, maybe no. So anyways, we'll do it with a geometric distribution. So here we keep doing something until the first time we succeed. So we'll focus on so we'll focus on just approaching it with a geometric distribution. So we'll answer this question directly. Okay, so we want to compute the expected value of B. What are we going to do? So it's the sum over the range of B. And then here, I know I'm dealing with integers, right? So instead of writing this, I'm just going to say it's integers. So I know I could have 0 boys, right? So it's 0, it's integers from k is equal to 0, infinity, because I could go on forever, of k times the probability that x is equal to k. So here I just did the range part kind of under the table. Right, the range is from 0 to k. Yeah, poor family.
0 or 1?
Okay, so now the hard part is usually to deal with this probability part. But to be honest, in this case, it's not that tricky. It's something that we've, I think, done repeatedly. So what is the probability that x is equal to k? So if I have exactly k boys, what needed to happen? And yeah, the idea is if I have k boys, well, x is equal to k if and only if what? So x is equal to k if on the kth child or k plus 1 child, which child will give me, I want a girl, right? So on what, how many child do I have in total? If I have k boys, I have k plus 1 child, right? If and only if I have k boys followed by a girl. Right? So okay. So now what do we do? What is that probability? Well, that's easy to deal with, right? That was a half of happening times a half times a half times a half. So that's 1 over 2 to the k times a half for getting the girl. So we cannot forget about the girl. Right? So it's 1 over 2 to the k. I hate when it does this. To the k. 1. So k boys followed by a girl. Okay. And now we just plug this in our summation. So I think it's much easier than what we just dealt with. K is equal to 0 to infinity. Infinity of k times the probability of 1 over 2 k. Now let me just share a useful identity. So if you're not sure in the exam how to simplify this, you can always use Wolfram Alpha. There's no problem with that. But this simplifies. You should be able to simplify this. Let me just maybe make a new share and show you guys the formula. So one more formula that you might want to take notes for, this formula. So you guys can see this. Yeah, so you aren't, okay. So, but can you guys see this share here? Okay, so try to memorize that formula. It's extremely useful for geometric distribution, right? It's very, very, very useful. So note it just, you have to be careful. It starts at 1. That's the only thing that you have to be careful about. So if I wanted the 0 term, well, I would have to add a k, right? Anyways, I think it's a worthwhile formula to remember. In any case, the this summation simplifies to something nice. So if you don't know what that is, well, you're kind of stuck on the exam. So I think, did he tell you? Usually that's the thing. I'm not sure. I cannot say anything about the exam, sadly, because I don't know anything. But do you know if he's giving you formulas? Because usually in Pat's exam and all the exam I've TA'd for, there's always at least 3 formulas. There's a formula for geometric variables, there's a formula for binomial theorem, and there's a formula for binomial distributions. So do you guys know if he's giving you?
You said we have to memorize all the formulas.
Okay, that's to me it's a pointless thing to memorize these formulas, especially when you're dealing with various situations. So yeah, so I'm much more a fan of comprehension and then memorization. Um, I'm not sure, but yeah. So it's a bit odd that they're asking you to memorize these formulas. Uh, like yeah. So I guess these formulas. So I think there was one question, right? So I'm confused as to why we can't use the expected value of a random variable that follows the geometric distribution. So you're correct. So the thing is, what is the so you're correct, and like we are going to do this, but hold on, okay? For the girl, that's what we're going to do, right? For the girl, we will be doing that. But what about the boy? So here, what if we do the expected value for the girl? What will we get? The girl is the easiest one, right? The expected value for the girl, well, you can, in the exam, this you can do. You can say, well, we note that we note blah blah blah. What do I want to say? Oh yeah, we will note that J follows or is a geometric variable. Probability success is equal half. That's so the expected number of girls that they'll get. Here it's actually, no, it's dumber than this, right? They stop having children as soon as they have a girl. So here, the expected value is much easier. So here it's simpler than that. It should be 1, so it's not quite 1, right? What is the range of G? There's only 2 values. Exactly, I was counting the total number of children. That's exactly what I was doing. None or 0, exactly. So here it's 0 times the probability that I get 0 girl plus 1 times the probability that I get 1 girl. Now don't be confused. The probability that I get 1 girl is what? It's 1, exactly. I need to have, like, I will stop eventually. So here, it's a good question. Are we convinced by this equality? Yes or no? Yes, right? So why do I know that what is the probability that I get a girl? Well, I only stop because I have to get a girl, exactly. Right? I stop as soon as I have a girl. So what is the probability that right? So this has to happen. The number of girls is 1, has to happen. Okay, which brings up an interesting question. So can I find in some easy way yeah, no, okay. So here you got 5/2. Is that what you said for the expected 5/2? This looks odd to me, but I guess you're right. So again, here the justification, it would be enough, I think, to say, okay, well, they only stop if they have a girl. Like, it's guaranteed. They have to have exactly 1 girl. Now, what's bothering me is that the probability that you have 1 girl is the probability of stopping, right? Is this not correct? Oh, let me check. Yeah, okay, that makes more sense. So I think you might have done a mistake here. So sorry, this is supposed to be k plus 1. This becomes 1. And I was looking at your 5/2 and was getting very confused. Yes, we will cover 7.8. So actually, this expected value is 1. And the reason is pretty simple, right? You can pull a half in front of it, and now it's just a geometric distribution, which you know is 1/2, which is 2. So it's 2 times a half, which is 1. And now that makes a bit more sense. I was really panicking now. So when you plug this in Wolfram Alpha, it should give you 1, right? Oh, for me it gives 1. It doesn't give 2 for me. And it makes sense, okay? So here, so the expected number of children that you would have is 2. That follows a geometric distribution. Now, the expected number of children that you get is equal to the expected number of girls plus expected number of boys. So another way to answer this question would have been to do the following. So the expected, or consider the x to be the number of children. Yeah, the number of children until the first girl. That's inclusive. Now this follows a geometric distribution with probability of success is equal to a half. This follows a geometric distribution with probability success equal to a half. The expected value of x is equal to 2 in class. And now what you note is that the expected number of children until the first girl, that's including the girl itself. So as a function, x, note that x is equal to j plus boy. So that's why I really brain farted when you gave me 5/2. I was kind of sweating. Like this and this is supposed to be given to. So note that this is true, and so therefore the expected value of x is equal to the expected value of girls plus the expected value of boys. And now which means, well, this is clearly 1. So you don't even need to go through there. You could just say, well, this is 2 by geometric distribution. This is 1 because they have to have a girl. And so this needs to be 1. So that would be another way.
I'm sorry, how did you get expected value of x equals 2?
So that's a theorem seen in class. So when you have a geometric random variable with probability of success p, the expected value of that random variable is 1/p. So that's, maybe I can write this. The expected value of such a variable is 1/p, which is 2 in this case. So that's a theorem that you have seen in class. And so you can make use of that theorem. Again, there was nothing wrong with dealing with the definition, but here there was a way to avoid this. Any questions about this one? I'm getting a bit tired to just look at geometric random variables. I want to move on to.
So the probability of x is just whether the kid is equal to, the kid is a boy or a girl, correct?
So x, sorry, what did you say? The probability of x?
Yes, the probability of x.
What do you mean by probability of x?
Like how you said, the formula for the expected value of x is equal to 1 over the probability. So that means that does that mean the probability of x is equal to whether x is equal to being a boy or a girl? Or
yeah, so here x is the number of children until the first girl. So it's the total number of children, the total number of trials that I made. So in a geometric distribution, you keep doing something until your first success. Well, here our success is having a girl. In a geometric distribution, the expected amount of trials that you needed until your first success is 1 over your probability of success. So the notion of success here is having this girl, this first girl. So this part is something that you have seen in class. Okay, so I feel like I've really slowed down in the past few questions, which is not good. I think starting to brain fart. So I'll actually take a 10 minutes break. And then I'll come back fresh. Okay, so I'm not sure if I'll do this one. Yeah, I'm not sure if I'll do this one. There's only this one and question 8. No, I'm going to post them. So again, I'm not sure if I want to do this one. Yeah. So break time. So we'll come back at 5:35, and that will be it. So we'll come back. So break time.